Let's try to apply these properties considering some examples. And let's see that these properties actually make our job much easier. The first application maybe that is important is the Laplace transform of, let's say, cosine of omega t. Of course, when I mean the Laplace transform of cosine of omega t, what I actually mean is the function that is 0 for time t less than 0, and then is a cosine for t that are non-negative. So this is cosine of omega t, but only for positive t's. So if we applied our definition on this, it would be a little complicated, because we'll have to compute the integral from 0 to plus infinity of cosine of omega t exponential of minus st, and this is not really I mean, we can compute it. I'm not saying that this is not computable. It's not difficult either, but we can do that with much less pain. So I just want to remind you that the cosine of omega t, for people who haven't seen complex analysis, can be written in this way as exponential of I omega t plus the exponential of minus I omega t divided by 2. The reason for this identity is that the exponential of I omega t, if you have seen complex analysis, this is just a refresh, otherwise you may be surprised by this. I'm still surprised by this property. The exponential of I omega t is given by the cosine of omega t plus the imaginary unit exponential sine of omega t. So when you take the exponential of I omega t, you take this quantity here. The exponential of minus omega t, using the same formula, we are simply replacing t with minus t, becomes cosine of omega t or minus omega t. They give you the same cosine, so we can keep it like this. Instead, the sine of omega t, the sine is an odd function, so we get a minus in front of everything, and we get sine of omega t. So these two relations here, coming from complex analysis, give us a way to compute the cosine of omega t, or represent the cosine of omega t as the sum of these two imaginary exponentials and dividing by 2. So if this is true, actually then instead of computing this by the definition, we can simply compute the Laplace transform of cosine of omega t as a function of s as 1/2 the Laplace transform of exponential of I omega t plus 1/2 the Laplace transform of the exponential of minus I omega t. And we have already computed the Laplace transform of the exponential, if you remember, if you see in our previous examples, we had seen, sorry if I'm scrolling so fast and I'm giving you zoom sickness, but the Laplace transform of the exponential of at is 1 divided by s minus a. So let's go back slowly here, and so this is given by 1/2, because now we are applying linearity, so we have just applied linearity. This can be written as s minus I omega, because I omega is equal to our a, plus 1/2. Now a becomes minus I omega, so this can be written in this way, s plus I omega. So we can write this in this way, 1 divided by this, s minus I omega, s plus I omega, and then we are left with s plus I omega plus s minus I omega, and this is equal to 1/2. Here the two imaginary terms cancel each other out, so we are left with 2s divided by, and now we have the difference of two squares, so this is given by s, and the square of I omega is minus omega squared. There is a minus as well, so this becomes plus omega squared, and so this can be written as s divided by s plus omega squared. So in this way we have computed this Laplace transform with absolutely no problems, because we have used already known Laplace transforms. Let's consider another case, so another example that is going to make our life, where we see that we are going to make our life easier if we use the right properties, is the Laplace transform of sine of omega t. Well, we could do the same thing here. We could represent sine of omega t using this formula, but why should we? We know that the derivative of sine is cosine, and that the derivative of minus cosine is sine. So we know this, that the derivative with respect to time of cosine of omega t is minus sine. So if we take the derivative of minus cosine of t, this is going to be sine of omega t, but let's remember that we are also multiplying by we need to multiply by omega. So if we divide this by omega, we find that the derivative of minus cosine of omega t divided by omega is the sine of omega t. So we simply proceed by using the formula for the derivative. The Laplace transform of the derivative of minus cosine of omega t divided by omega as a function of s, this Laplace transform needs to be equal to the Laplace transform of sine of omega t as a function of s. So this needs to be, the derivative becomes a multiplication by s, so my s times the Laplace transform without the derivative of minus cosine of omega t divided by omega minus, and now we have to compute this function in t equal to 0, because that's what the derivative formula requires. So this is the cosine of 0 is equal to 1, so this is 1 by omega with a minus, so it becomes plus 1 by omega. Let's see what happens here. We have s, we have also a minus, and we have also a division by omega times the Laplace transform of cosine of omega t as a function of s plus 1 by omega. One last step, we have 1 divided by omega that multiplies 1 minus s that multiplies the Laplace transform of the cosine that we had here. So we have, here we had s squared and an s squared here. So here we have s that multiplies, we were saying, I forgot, s divided by s squared plus omega squared. So we have s squared that divides s squared plus omega squared, and this is given by 1 divided by omega that multiplies s squared plus omega squared minus s squared divided by s squared plus omega squared. And this is given by, in our last step, the two s's simplify each other, and one omega cancel the other omega, so this is given by omega divided by s squared plus omega squared. Again, much less pain than going through the definition.